This is a lecture on the Kennedy Class 1 removable partial denture design. The definition of a Kennedy Class 1 is a bilateral edentulous area located posterior to the remaining natural teeth. On the dentiform on the upper right, you can see that we have no modification spaces, but that doesn't mean that they can't exist in the Kennedy Class 1. This is your straight definition of the Kennedy Class 1. On the lower left picture, you can see a partial denture that is replacing the posterior missing teeth. So this is a typical Kennedy Class 1 partial denture design. This is one of the most common Kennedy Class 1 examples where you have just two canines remaining. The mandibular canines are the teeth that are the very last ones to be lost in the mandibular arch. Many patients are getting two mandibular implants to do basically what this RPD does. The RPD is retained by the two canines. If it were implants, it would have two abutments in the implants and then two attachments in the prosthesis to retain it. The denture is then called an overdenture and is no longer referred to as a partial denture. The supporting abutment teeth and the remaining ridges are subjected to various forces when an RPD is in function, especially the Kennedy Class 1. We're going to look at some of those forces and what parts of the RPD counteract these forces. The dentist must design the RPD considering the following with regards to force: the direction of force, the duration, the frequency, and the magnitude of the force all influence the success of the RPD. The Kennedy Class 1 partial exhibits composite support. By that, we mean that it derives its support from the teeth and it derives its support from the soft tissues and residual ridge beneath it. RPDs are designed using some of the basic principles of simple machines and the rules of physics. Some of these simple machines are listed above. They are the lever, wedge, screw, wheel and axle, pulley, and inclined plane. When we design a removable partial denture, we want to avoid creating a first-class lever when we design that partial denture because it's very destructive on our abutment tooth. We also want to avoid the inclined plane because we don't want to have our partial denture leaning on the sides of teeth and putting pressures to actually create a movement of the tooth away from the partial denture framework, as would be the case with the inclined plane. A lever is a simple machine. It's usually a rigid bar or rod, which is designated to rotate about a fixed point called a fulcrum. Our removable partials operate under some of the principles of levers. If you don't remember how this operates or how it works, go to the biomechanics lecture that's on Blackboard and refer to those principles. The partial denture will rotate in relation to the three cranial planes due to functional forces that it is under and because of the differences in the support characteristics of the abutment teeth and the soft tissues covering the residual ridge. The movement around the fulcrum may be small on the distal extension RPD, but the potential for lever-like forces on the abutment teeth is a factor that has to be considered when we design the framework. We will learn to do clasping mechanisms that help prevent torquing forces on these abutment teeth. These pictures exhibit the principles of levers. The force is placed at one end of the teeter-totter, and the resistance is at the other end with the fulcrum in between. In this example, the length of the effort arm from the fulcrum is 4 feet long. The length of the arm at the resistance end is only 1 foot. So the mechanical advantage is the effort arm of 4 divided by the resistance arm of 1, or 4 times. Therefore, we have a mechanical advantage of 4 to 1. So we can place a load on the resistance end that is 4 times the weight of that of the load on the effort arm, and it can be lifted easily on that teeter-totter. We can place 8-pound weight at one end, and we will be able to lift it with a 2-pound weight at the other. A cantilever is an object supported only at one end. It can act as a first-class lever. Cantilevers should be avoided both in FPD and in RPD. I feel like the only exception is when you have a lateral incisor that's going to act as a cantilever off of a canine. If the abutment is a very strong tooth and is not compromised from a matter of size, shape, periodontal condition, restorative condition, or occlusal condition, then this may be an acceptable use for the cantilever. In this example of the Kennedy Class 1, the fulcrum is our rest that's placed on the abutment tooth, and the clasp tooth is the resistance at that end of the direct retainer arm. The longer the arm is on the force side, the greater the force on the resistance side, which is our tooth. We strive to minimize this force on the abutment tooth by designing clasping mechanisms that create less stress on that abutment tooth. If resorption takes place under that distal extension, then the first-class lever forces will be transferred to the abutment teeth, which can be very detrimental to that particular tooth. As that occlusal load goes down, the more room there is because of resorption, the greater that problem will be on the abutment tooth. It is not uncommon that the axial surfaces of the abutment teeth need to be altered to locate components of the clasp assemblies in a favorable position. We wish to counteract off-vertical forces applied to the tooth. If you've ever tried to remove a fence post from the ground or something that was buried in the ground, you found that you could wiggle a post out of the ground more easily if you grabbed the post high up off the ground, away from that center of rotation. The lower you were positioned on the tooth toward the ground, the more difficult it was to get any movement from that post. This illustration shows how this concept applies to the direct retainer placement on a tooth. Sometimes we have to alter the axial contours to get these favorable results where we lower the axis of rotation. The tooth in the upper picture will be subject to more damage from off-axis vertical forces than the tooth in the lower picture, where the direct retainer is lowered closer to that center of rotation or fulcrum line. Let's look at the various movements that a Kennedy Class 1 RPD might make under various forces. The first is rotation around the fulcrum drawn through the most posterior abutments, through that canine and that second premolar. When the patient bites down, the anterior of the partial denture wants to lift up as it rotates around the fulcrum line. That major connector in the front wants to lift up. The second movement is when the patient eats sticky foods on the extension bases. The partial wants to lift upward in the posterior area as it rotates around that fulcrum line. The movements shown in the previous slides are resisted by 1, the tissues of the residual ridge, 2, the indirect retainers, and 3, the retentive clasp on the abutment teeth. For movement number 2, it's the rotation about a longitudinal axis as the distal extension moves in a rotary fashion about the residual ridges. Look at the arrows that show this rotation around each axis. This second movement is resisted primarily by the rigid quality of the major and minor connectors that are on the lingual of those remaining natural teeth. They are substantial enough to resist this torquing force. The third movement is rotation about a vertical axis located near the center of the dental arch. The rotation is a full circular type of movement, as shown first. This movement number 3 is resisted by the stabilizing components, that is, the reciprocal clasp arms and the minor connectors that are in contact with the vertical surfaces on the lingual sides of the teeth. With regard to horizontal movements, you're going to always have horizontal or lateral movements occurring during activities like mastication, clenching, and bruxing. You really can't get around that. The best treatment for horizontal movement is to construct an occlusal scheme that is harmonious with the rest of the natural teeth. All lateral interferences have to be eliminated during the eccentric movements of the jaw. On the extension base removable partial denture, be it Kennedy Class 1 or Kennedy Class 2, on the edentulous side that has no tooth posterior to it, you must utilize a clasping system that is kind to the abutment tooth and that prevents torquing of that tooth over time. Here at ULSD, we're going to use 4 clasping systems on the extension base area of removable partial dentures on that abutment. They are the RPI system, the modified T-bar, the combination clasp, and the reverse circlet or the interproximal ring clasp. Listed on this particular page are the 4 clasping methods that will be used for the extension base RPD. We will go into further detail on each one of these as we approach the next few slides. The 4 components of the RPI clasping system are 1. Mesial rest, 2. Distal proximal plate, 3. The I-bar, and 4. You drop down on the lingual between the distal proximal plate and the mesial rest. Reciprocation is provided by the minor connector leading up to the rest and the distal guide plate extending lingually just past the contour of the tooth where it becomes a little smaller. The purpose of this is to trap the tooth from moving lingually when the retentive arm flexes into the undercut. The RPI is used when there's a 0.01 midfacial undercut and when there is no contraindication to the use of a bar-type clasp. This slide shows a drawing of the I-bar, and it shows that I-bar first engages the tooth or touches the tooth at the 0.01 undercut. And then a pod is created where the I-bar from the point of touching the tooth extends upward along the surface of the tooth for another at least 2 millimeters. So this provides a little pod where it's not just the point or the tip of the I-bar touching, but an area of 2 millimeters that touches the tooth up to the survey line. The specifications of the I-bar are as follows. It originates from the edentulous base attachment and usually from one of the cross struts of the base attachment to enable a good casting of the metal. If meshwork is used, it originates about at least one tooth width posterior to the natural tooth. The important thing to remember is that its length and its dimensional thickness are 2 factors that affect flexibility of the bar clasp. It tapers from its origin and becomes horizontal to the ridge, and at the point at which it emerges from the base, it's about 2 millimeters in thickness. It should cross the marginal gingiva at a rounded right angle and touch the tooth at its 0.01 undercut. The tip is usually formed as a pod and is usually approximately 1.5 to 2 millimeters in width and 2 to 3 millimeters in height, which may extend slightly above that survey line depending on where the undercut is located. This slide illustrates that the guiding plane is prepared through an area of 2 to 3 millimeters from the marginal ridge downward. The guiding plate is placed 1 millimeter above the bottom of the guide plane that you just prepared and touches the tooth through an area of at least 1 millimeter in height. The laboratory will prepare the cast, providing a 4 millimeter opening beneath the guide plate in the apical area. This space allows for food and debris to escape and not to be jammed into the sulcus. This space also allows the partial to depress in that posterior area under masticatory forces, and the guide plate then rotates toward the tooth over this spaced area, but does not torque the tooth. The framework rotates around the mesial rest toward the long axis of the tooth, and the I-bar actually disengages the tooth. Therefore, you do not get much torque on that abutment tooth. This is the whole idea of the I-bar. A view from the lingual aspect of the RPI clasp system reveals a mechanism for reciprocation for the clasp assembly. First of all, the guide plate extends lingually past the buccolingual height of contour on the distal surface of the tooth, and it functions to trap the tooth from moving to the lingual when the I-bar flexes into the 0.01 undercut. The minor connector also aids in this reciprocation action. Working in conjunction with the mesial rest and the minor connector leading up to it, the guide plate extends lingually to where the tooth becomes a little bit smaller, thus trapping the tooth from moving lingually as the I-bar flexes into an undercut. To reiterate how the RPI system works, when an occlusal load is placed on that extension base area where there's no posterior tooth, that depresses into the tissue. That space between the guide plate where it touches the tooth and the gingival area actually closes up because the plate rotates into that area. At the same time, the I-bar disengages the tooth by moving downward and forward like the arrow shown on the illustration. And the mesial rest rotates upon itself, thus producing forces down the long axis of the tooth and not off-axis forces. This is the kindest system to use on an extension-based partial and should be used whenever possible. One of the 4 clasps for use on the distal extension removable partial denture is the modified T-bar clasp. It has an embrasure rest on the mesial of the abutment tooth next to the edentulous area and a distal rest on the tooth just anterior to it. There is a distal guide plate, and the lingual drops away with the guide plate and the minor connector providing reciprocation in a manner the same as we discussed on that RPI slide. The T-bar is used when we have a 0.01 retention on the distal facial surface of the tooth and when a bar clasp is not contraindicated. Observe the different components of the modified T-bar. Point A is the horizontal part of the bar that originates from the strut in the base attachment area. It runs parallel to the crest of the ridge, and then at point B it makes a rounded right angle and goes straight up, and it should be at the middle of the tooth, mesial-distally. And as the bar passes the marginal gingiva, note that it is perpendicular to the marginal gingiva. The first point of touching at point D is above the survey line for this T part of the bar, and then the little retentive tip swings back into your 0.01 undercut. A good point of observation for this is to look at the lower illustration. The modified T-bar clasp assembly has an embrasure rest, which includes a mesial rest on the abutment tooth and a distal rest on the tooth just anterior to it. The modified T-bar has many of the same specifications of the I-bar, in its approach arm area, i.e. it avoids the marginal gingiva by 3 to 4 millimeters. The bottom border is 6 millimeters below the marginal gingiva. It's about 2 millimeters wide. It makes a rounded right turn at the middle of the tooth mesiodistally and engages the tooth at or above the survey line, and only the retentive component goes into the .01 undercut on the distal facial surface. The guiding plane is prepared to extend a minimum of 2 to 3 millimeters below the marginal ridge of the abutment tooth. The distal guide plate extends superiorly at least 1 millimeter above the bottom of the guiding plane.
A view from the lingual aspect of the modified T-bar clasp reveals the mechanism of reciprocation for the clasp assembly. The guide plate extends lingually past the buccolingual height of contour on the distal surface of the tooth. It, along with the minor connector leading to the rest, functions to trap the tooth from moving lingually when the modified T-bar flexes into the undercut on the distal facial surface of the tooth. The framework dips down to avoid the marginal gingiva by a minimum of 3 millimeters. The major connector must be a minimum of 5 millimeters wide at this point for strength of the prosthesis, or if that is not present, you must plate the tooth at the survey line.
Probably our second most popular system is the combination clasp, and the combination clasp consists of a wrought wire on the buccal surface that goes into a .02 mesiofacial undercut. It contains a distal rest, which is different from some of the others that we've had. Please note that. And there is a distal guide plate. For reciprocation, you can use most commonly the lingual plate, which is positioned just above the survey line. It can also utilize an arm that is a reciprocal component, or an arm that is also placed above the survey line. This particular clasp is used when you have .02 mesiofacial undercuts and some of the other undercuts that rule out the use of the I-bar. So it has a contraindication to a use of an I-bar when we use this wrought wire clasp. On this slide we have two illustrations of the combination clasp. On the left is the buccal surface. You can see that the wrought wire originates at least a centimeter posterior to the natural tooth where it is soldered to the framework in the base attachment area. That wire comes forward, and basically on the lingual aspect of the guide plate, it turns up to the occlusal surface, and then it originates from the occlusal, coming down above the survey line, but about halfway it will go under the survey line into a .02 undercut and come back up the side of the tooth in sort of a J-shaped, or in this case a backward J, or reminding you of a ski jump area on a slope. It goes down and then the skier goes back up in the air and off the edge of that ramp. So this provides more retention if we have half of it under the survey line and this J sort of shape. On the lingual aspect, we would have a reciprocal arm that is a cast circumferential originating at the distal rest and coming forward all above the survey line at least 1 millimeter and approximately in the middle third of the tooth. Please note that the wrought wire has a distal rest, which is different from our others. The last clasping system that we'll talk about using at ULSD is the reverse circlet clasp, sometimes called the interproximal ring clasp. This particular direct retainer engages a .01 distal facial undercut, and it originates from the suprabulge area of the tooth. It has a mesial rest, a distal proximal plate, and either reciprocating component can be lingual plate or a lingual arm. The fourth acceptable clasp for use on the extension-based RPD is the reverse circlet clasp, or another name is the interproximal ring clasp. It has normally a mesial rest. Sometimes we might put an embrasure rest when there's a possibility of wedging between the two teeth. The direct retainer is a cast circumferential clasp that's origin is drawn on the survey line and then it dips into a 0.01 distal facial undercut. The guide plane and the guide plate are prepared as in the previous clasp assemblies that we discussed. The reciprocal component is also a cast clasp arm that is drawn on the survey line. The partial dips 3 to 4 millimeters below the marginal gingiva, and the lingual bar at that point must be a minimum of 5 millimeters in width in order to provide strength for the prosthesis. If there's insufficient room, we plate the tooth at the survey line. We can use a bar clasp except when the following contraindications exist. If there is a tissue undercut of greater than 1.5 millimeters at the inferior border of the approach arm, the bar would be contraindicated because the bar would stick out and the mucosa of the inner cheek under function would rub against the bottom of the bar and be irritated. We can also not use the bar if there's a real high frenum attachment because the function, when the frenum or the muscle is in function, it would drag along the bottom of the bar and it would be cut. If the tooth is extremely bulbous, then it is highly likely that that bar would extend out into away from the mucosa and cause the same problem that we talked about with an undercut greater than 1.5. That's also true when the tooth is very buccally inclined. The last contraindication would be if we don't have an undercut at the appropriate surface of the bar we're intending to use, then we cannot use that bar. Here's the first situation that we talked about. If the bar stands out from the tissues, it catches the cheek and causes an irritation. Note the large bony protuberance, which causes the bar to have to be placed out farther, and at that 6 millimeter mark below the marginal gingiva, it's standing out greater than a 1.5 millimeters from the tissue. This would be a contraindication to the use of the bar clasp. At the bottom of the approach arm of the bar clasp, the modified T on this case, there is a frenum that's very noticeable on the dentiform cast. Luckily, you can contour that bar, and the way it turns at a 90-degree angle, you can avoid that frenum attachment on our cast. But if you cannot avoid that frenum attachment, then that's a contraindication for the use of a bar clasp. It doesn't take just a bony undercut to cause this problem of the bar having to stand out away from the tissues. A very bulbous or labially inclined tooth can have the same effect. That bar has to clear that area, so it has to stick out at least the amount of the bulge on the tooth. And if at 6 millimeters below the marginal gingiva, it's out past 1.5 millimeters, then it's contraindicated for the use of the bar. An obvious contraindication to the I-bar is when the tooth does not have a 0.01 undercut on the midfacial or slightly to the mesial of the midfacial of the buccal surface. It may be necessary to alter that tooth through preparation or create a restoration with the undercut prepared in it, like with a crown. And lastly, if a tooth lacks a 0.01 undercut in the midfacial in the cervical third, it cannot be used as a I-bar recipient. Usually, you can cut a 0.01 undercut into the tooth in order to create that little undercut for retention. But some instances, if it's really thin enamel and it's really, really close to the gingiva, it makes it difficult to make that transition. When doing any of our clasping with circumferential type clasp, we must remember the principle of encirclement. The clasp arms must encompass more than 180 degrees of the greatest circumference of the crown of the tooth, while passing from the superbulge area to the infrabulge area to that designated undercut. This prevents the tooth from escaping the clutches of our clasp assembly. The length of the clasp arm also affects the flexibility of the clasp arm. In all reality, we usually place the arms from the beginning area of the tooth to the opposite line angle of the tooth surface. That is, direct retainer that originates at the mesial-facial surface will extend to the distal-facial line angle of the tooth. The same would be true if a reciprocal component is placed on the opposite side of the tooth. It would not end at the middle of the tooth. Think about a large beach ball that you have surrounded with your arms for a greater than 180 degrees of its circumference. What happens if you squeeze the ball? It cannot pop out of your arms. But if you only encircle it by less than 180 degrees and you squeeze that ball, it can pop out on you. The principle of encirclement applies to the bar clasp also. You must have at least 3 widely spaced areas of tooth contacted by metal to embrace more than 1/2 of the tooth circumference. There are several other types of bar clasp, but we were concentrating only on 2 of them. They are usually named for their shape. You will find the I bar, Y, and T bar in the literature and in your text. Investigate these bars and review the rules of where the components are placed in relation to the survey line, so that you may be prepared for any type of board examination that would be asked on them. Here are some other clasping mechanisms that you should understand, but they're not generally accepted as the ones we're going to use on an extension-based partial. We concentrate on a few clasping systems, but these may appear on a board examination for you. The hairpin, or reverse action clasp, is another clasping system that may be used, but is not one of the preferred systems that we use here at ULSD. The hairpin clasp originates and ends on the same surface of the tooth. It may originate with the first half of the direct retainer above the survey line on the superbulge area. It then reverses its direction at the middle of the tooth, and the terminal half of the clasp arm approaches the undercut in the infrabulge area. The problem with this clasp is that when the force is applied to the extension base, the direct retainer, which is above the survey line at its origin, places a force on the tooth at this position. If the distal rest is used on the tooth, the force can direct movement of the abutment tooth toward the posterior edentulous area. This movement can be somewhat counteracted by placement of a rest on the mesial aspect of the tooth. The direct retainer would then have to originate off of the guide plate, which must extend up to the marginal ridge. We don't use this very often. Every Kennedy Class 1 RPD will have to have indirect retainers. Usually you may find 2 on the indirect retainers. An indirect retainer must be located as far as possible away from the distal extension base or the fulcrum line. On this particular case, if we drew a line through the fulcrum line, then ideally we would want to have a perpendicular to that, and so we would be choosing central incisors if we had them for our indirect retainer, but which we don't. So if you look at those other 2 little arrows, those are vectors going out, splitting that space, and it would call for indirect retainers on number 6 and number 11 as far as our canines. So those act as indirect retainers. If they weren't indirect retainers, they would still be necessary because you must have a rest next to or near every edentulous area. And with that edentulous area, 6 and 11 are the most ideal to put rests to support those teeth that will be added in that area, but also it acts as an indirect retainer.
For indirect retainers that are placed on this particular dentiform, we first draw a line through our fulcrum line. Those are the two posterior abutments on this arch. Then we drop a perpendicular to that, and it would cross at number 24, number 25, our central incisors. But on the mandibular arch, we do not place rest or indirect retainers on any of our incisors. So we drop a little vector from that point, and the nearest position that we could place them would be on number 22 and 27, which would be incisal rest. On this particular case, we're showing the indirect retainer on number 21 in the mesial. This is a more appropriate position because it's not that far from the actual canine incisal rest, but there usually isn't a lot of occlusion in that area, so we have to do minimal reduction of the tooth, whereas on number 22 and 27, we may have to reduce sufficiently in order to clear enough room for those incisal rests. So oftentimes, instead of using that number 22 or 27 canine, we move over to the mesial fossa of the first premolar. Now, we don't on number 27 because that would be too close to the distal rest on that tooth, and our rule does say to try and separate the spacing between our indirect retainer and the fulcrum line as much as possible.
The indirect retainer must be on a tooth that is capable of supporting the function of an indirect retainer. Therefore, on a mandibular, you're not going to have any laterals or central incisors with rest on them. They're not very strong. So what we do is move over to the next closest tooth, which happens to be the canine rather than the lateral incisor, because the incisors and centrals are not used for indirect retainer rest. To summarize some of our rules of Kennedy Class 1 RPD design, 1, you're going to place a clasp assembly on each tooth next to the edentulous area through which the fulcrum line traverses. Therefore, there'll be 2 clasps. You will select one of 4 clasp assemblies that is recommended by ULSD to relieve stress on the abutment teeth. 3, a rest is going to be placed next to or near each immodification space if they exist in the arch. Usually there'll be 2 indirect retainers that are placed as far away from the fulcrum line as possible. On this example above, the rests on tooth number 22 and 27 are necessary because we need a rest next to each edentulous area, but they also act as indirect retainers. The canines often have bony undercuts, which negate the use of the eye bar because it would stand out too far away from the tissue, or any other bar for that matter. Our second choice would be the wrought wire clasp because of its flexibility, and it goes into a .02 mesiofacial undercut. Another option would be the cast round clasp, which goes into a .01 undercut. The cast circumferential is not as acceptable because it is very, very rigid, and it is used only if the undercut is in the gingival third and the other options do not exist for us. The maxillary is much more acceptable for the cast circumferential due to the large amount of support by the major connector from the palate, and thus that palate prevents torquing of that tooth. You also have to think about the condition of the tooth periodontally. You want to look at the length of the root. You want to look at the length of the tooth as a whole because there are some short, stunted teeth. And you need to look at the actual restorative condition of that tooth. The finish lines are placed where the plastic joins the major connector. The mandibular finish line comes down the distal lingual line angle of the tooth and slants distally, forming an acute angle. The internal finish line is actually anterior to the external finish line on the undersurface of the major connector. The acrylic joins this finish line and it extends to cover retromolar pad and extends into the retromylohyoid fossa. The finish lines are placed where that plastic joins the major connector. The maxillary finish line comes down at the distal lingual line angle of the tooth, and it pretty much parallels the ridge, but it leaves enough room to set a tooth, at least the size of the tooth that it's replacing, and have about 2 to 3 millimeters of acrylic on the lingual of it that is all in meshwork. It forms a nice butt joint with the finish line as shown in the lower picture of the slide. The finish line goes back to almost to the hamular notch area, but it allows enough room so that the coverage through the hamular notch is that of acrylic, so as to make adjustment easier in that area. The base attachment is actually a minor connector as far as one of the component parts of the partial. It's attached to the major connector and to the guide plate, and it extends about 2/3 of the distance from the distal abutment tooth to the beginning of the retromolar pad. It does not exceed 25 millimeters because of the large lever arm it would then create and have a greater possibility of fracture. It does not extend past where the ridge starts to make a dramatic turn upward. You don't want base attachment to be on a slope. It interferes with the setting of teeth. The mandibular also has a processing stop at the end of the base attachment, and this helps with keeping the framework in position when the processing takes place and the acrylic is packed under high forces of pressure. The base attachment on the maxillary arch extends very close to the hamular notch. Our Phoenix text says that there is a processing stop on the maxillary arch. The major connector can act as a processing stop to some extent, but it does not hurt to put that processing stop also on the base attachment area. The mandibular major connector that we have not drawn is the lingual bar, and it's preferred if there's at least 8 millimeters of space between the marginal gingiva and the functional floor of the mouth. When this one is drawn, you have to avoid the marginal gingiva by 3 millimeters, and the bar itself should be a minimum of 5 millimeters wide. Hence, that's how we come up with that 8 millimeters of space that's needed for the lingual bar. Also, to do the lingual bar, you should have sufficient number of posterior teeth remaining to help give support for that major connector. If the teeth are periodontally involved in the anterior area, then you would prefer using a lingual plate rather than the lingual bar. If there's insufficient space or less than 8 millimeters of space between the functional floor of the mouth and the marginal gingiva, then the lingual plate has to be used. If there are questionable teeth from a periodontal standpoint, the lingual plate should be used because correction and adjustments to the denture can be made if teeth are lost, if these teeth have been plated. The most common maxillary major connector found in the Kennedy Class 1 is the anterior posterior palatal strap major connector. The fewer the teeth remaining in the arch, though, there's a greater chance that it will have to be a palatal plate major connector. Patients like to have an opening in the palatal area. The anterior and posterior strap must be a minimum of 8 millimeters in width. The anterior border should avoid the speech zone at its borders, and the posterior strap cannot extend posterior to the vibrating line, or food and debris and water will get up under it. The hole must be at least as large as a nickel in the palate, or it should not be placed. A hole in the palate that is smaller than a nickel is actually very annoying to the patient.